So far in this chapter, we have discussed the Schrodinger equation and the time evolution of a quantum mechanical state. We have seen that we can describe time evolution in quantum mechanics as the change of state with time. In this section, we shall see that there are different ways of approaching time evolution. In particular, we shall talk about the Schrodinger and the Heisenberg pictures of time evolution. In the first session, we shall talk a little bit about unitary operators and also introduce the Schrodinger and the Heisenberg pictures. So in the previous section, we introduced the concept of time development by considering the time evolution operator that affects the state gates. That approach to quantum dynamics that we already saw is called as the Schrodinger picture. Now there's another formulation of quantum dynamics where observables rather than state gates change with time. The second approach is known as the Heisenberg picture. So in quantum mechanics, we have got states and we have got observables like P, H, X, etc. These are Hermitian operators. Okay. So what we saw in the first section was that we can talk about time evolution as the change of state with time, right? The state changes to another state with time. This is called the Schrodinger picture. So what we have actually discussed so far is time evolution in the Schrodinger picture. But we can also talk about the change in operators, right? We can think of states as not changing and operators as changing in time, right? And this approach is known as the Heisenberg picture. Before discussing the details of the differences between the two approaches, let's talk a little bit about unitary operators. Let's make a few general comments. We have already seen that unitary operators are used for different purposes in quantum mechanics. We have already used unitary operators in different contexts. For example, in the first chapter, we introduced the unitary operators in the context of a change of representation or relating different representations. Okay? Because we know that we can choose different bases. We can choose different bases when we talk about quantum mechanics. Okay? Specifically, we know that we can use the eigenkets of any Hermitian operator as the basis. All right. And we can represent the states and the operators in different bases. And then we ask the question as to how are these different representations related. Right. For example, you can represent the same state in this basis or in a different basis. Right. We would be using different column matrices to represent the same state get. Now, how are these different representations related? And over there, we saw that these representations are related by unitary transformations. So in the first context where we used unitary operators, we were talking about representing the same state get in different bases, all right, or the representations of the same state get. Here, there's no change of state get involved. Okay, we are just relating different representations of it through unitary operators. And then we talked about two unitary operators that actually act on the state and change it. For example, we talked about the translation operator and the time evolution operator. In both cases, we had the state changing to another state. Okay. Here, U acting on ket alpha is the state get corresponding to a physical system that actually has undergone translation or time evolution. In this case, U could either be the translation operator or the time evolution operator. Both were unitary. Okay. Now, we shall denote the translation operator as T of dx vector or T of dx vector prime, where dx vector prime is an infinitesimal translation. Now, if you remember from the first chapter, we used this notation for the translation operator. All right. I called this as J of dx vector prime, but actually it's T of dx vector prime. It's T written in a weird way. So instead of this, I shall change the notation to T of dx vector prime written in this way because this is easier to write. So I hope this change of notation will not cause any extra confusion. Okay. Now also in the textbook, the time evolution operator is written in a slightly weird, in the form of a slightly weird U like this. All right. So we shall not use that notation. Instead, we'll simply write a capital U for the time evolution operator, U of t comma t0. Okay. Now again, in some places we might use this U for the time evolution operator. All right. So this need not cause any confusion. We are just using a convenient notation. because some of the later sections I have already recorded, and in that the notations may be different, right? So this need not cause any confusion. This or this, it's the same translation operator. This u or that other u, these are time evolution operators. All right. Now here we have used u for general unitary operators. For time evolution operator, we'll write u of t comma t0. Okay. Now we are also familiar with the important property that unitary transformations preserve the inner product. All right, we have talked about in detail when we talked about the conservation of distinctions in the case of time evolution. All right, also in the case of space translations, we said that the total probability has to be conserved, or the normalization has to be conserved. All right, now all this is made possible because the inner products do not change when you make a unitary transformation. All right, for example, suppose the state beta goes to u get beta, all right, and the state alpha goes to u get alpha. It's the same transformation on both these states. All right, now suppose you want bra beta get alpha, right? From here we can find the corresponding bra beta is equal to bra beta goes to bra beta u dagger. Okay, so this inner product of bra beta and get alpha goes to bra beta u dagger, because bra beta goes to bra beta u dagger, and get alpha goes to u acting on get alpha. Now since by the unitarity property u dagger u is the identity operator, so this is simply bra beta get alpha. So the inner products are preserved. Preservation of inner product is an important property of unitary transformations. So the unitary operators that we introduced actually act on the state and change the state. All right. So we see that get alpha goes to another state, u acting on get alpha. Right. Now since these transformations affect the state gets and they don't act on operators, we can find how an inner product of this form must change. Bra beta x get alpha. Right. We shall be seeing such inner products when we talk about the matrix elements or expectation values. For example, expectation value of operator x in the state alpha is given by bra alpha x get alpha. It's an inner product of this form. So we are interested in knowing how such a combination changes under a unitary transformation. Let's look at it. All right. We are looking at bra beta x get alpha. We already saw that bra beta goes to bra beta u dagger under a unitary transformation u. Okay. And get alpha goes to u acting on get alpha, and there's no change to the operator. All right. So we see that bra beta x get alpha goes to, we'll write this as bra beta u dagger, because bra beta goes to bra beta u dagger. All right, and multiplied by operator x multiplied by u acting on get alpha. Okay. Now we have talked about the associative property. Since these multiplications are legal multiplications, right? We can get rid of these brackets and these dots, and we can write this as, this is equal to bra beta u dagger x u get alpha. Okay, so this is how the inner products of this form bra beta x get alpha changes under a unitary transformation. Okay, again using the associative axiom. Okay, an inner product of this form can also be written as bra beta dot u dagger xu dot get alpha, because all these are legal multiplications. It doesn't matter which multiplication you carry out first. Okay, so the same thing can also be written as bra beta multiplied by u dagger xu multiplied by get alpha. Now we immediately see that this change, all right, bra beta x get alpha going to bra beta u dagger xu get alpha, all right. This change can be interpreted, or this mathematical relation can be interpreted in two ways. Okay, in the first approach, this is the approach that we have been using. We can say that the state gets actually change under this unitary transformation, and the operators remain unchanged. Okay, in that case, we put the brackets here. All right, the states change and the operators remain unchanged. All right, the x operator is unchanged. Okay, in the second approach, you could also interpret it you can also interpret this as the state remaining the same and the operator changing according to this equation. Okay, so in the second approach, you can also interpret this as x going to u dagger xu with state gets unchanged. Okay, in any which way you interpret it, the final result is the same. Bra beta x get alpha goes to bra beta u dagger xu get alpha. Okay, so let me repeat. The first approach is where the state gets changed under the unitary transformation and operators remain unchanged. Okay, or we can talk about a situation where the operators actually change according to this equation and the state gets remain unchanged. Okay, both are mathematically equivalent. In classical physics, we did not have any distinction between states and observables. Okay, so we did not introduce any state kits, but still we had to talk about translation, time evolution, etc. Now, how did we do this in classical physics? In classical physics, we said that time evolution, translations, etc. actually changed the quantities x vector, L vector, etc. Right? We talked about how these quantities changed under certain transformations, whether translation or rotation or time evolution, etc. Okay. So maybe we can find a closer connection between quantum mechanics and classical mechanics if we use approach 2, because approach 2 looks more like classical mechanics. All right, at least it looks more similar to what we have done in classical mechanics. We therefore conjecture that a closer connection with classical physics may be established if we follow approach 2. A simple example may be helpful here. Let's go back to the infinitesimal translation operator written as t of dx vector prime, where dx vector prime is an infinitesimal displacement. Okay. Now we talked about this in the first chapter and it was based on approach 1. We said that state gets change under a translation. Okay, so this t of dx vector prime according to the first approach affects the state gets and not the position operator. So we see that get alpha goes to the infinitesimal translation operator acting on get alpha and operator x remains the same. Okay, so this is approach 1, get alpha going to t of dx vector prime acting on get alpha and x vector remaining the same, operator x remaining the same. Okay, so this is approach 1. Now, if we follow the second approach, the state remains the same. There is no change to the state. And the operator changes according to x vector operator goes to u dagger x operator u. Okay. So that's what we have here. In this case, u is the translation operator, which we denote as t of dx vector prime, where dx vector prime is an infinitesimal displacement. Okay. Now, this is the infinitesimal translation operator, as we already know. Okay, and this is t dagger. Now, how do we take t dagger here? We see that dx vector prime does not change because dx vector prime is an infinitesimal displacement. It's a vector which can be written as, for example, dx prime I hat plus dy prime j hat plus dz prime k hat, where I, j, k are the unit vectors along x, y, and z directions. Okay, so this does not change because this dx prime, dy prime, dz prime are small numbers. Okay, small real numbers. So this does not change. And p vector, we know that p vector is the momentum operator. It's a Hermitian operator. So p dagger is equal to p. That also does not change. The only thing that changes when you take the Hermitian conjugate is that I will go to minus I. Okay, that's why we have a plus here when we take u dagger, or in this case t dagger. Okay, so according to the second approach, x vector operator goes to t dagger x vector operator t. Let's now calculate this. Let's now carry out the multiplication. We see that x vector operator goes to, or the position operator goes to, we have to multiply this. So let's take the first term, it's identity operator multiplied by x operator multiplied by the identity operator. Okay, so it's just multiplying the x operator by identity operators on both sides, which gives you simply x vector. So x vector operator, the first term is simply the position operator. Okay, now let's look at the second term. The second term is obtained by this multiplication. First term multiplied by x operator multiplied by the second term in here. Okay, so that is identity operator multiplied by x vector is x vector operator is x operator itself. Okay, we have a minus sign here. Let me write it here. So we have got minus x operator and then I p vector dot dx vector prime divided by h bar. Now these are operator multiplications. You have to be careful not to mix up the order of multiplication because operators in general do not commute. So in this multiplication, first you have to write x vector operator and then the p vector operator. Okay, you cannot interchange this as we usually do with normal functions or normal numbers. Okay, you cannot do that. So you have to be careful where you put your operators. All right. Okay, let's look at the third term. The third term is obtained by this multiplication, the second term in here, x operator, and the first term in here. So that is simply I p vector dot dx vector prime divided by h bar and the position operator. There's one more term which you obtained from the second terms in each of these brackets. Okay, but this is higher order in dx prime, dy prime, dz prime, etc. Okay, you will get a square of the infinitesimal quantity. So this term can be avoided when we talk about infinitesimal transformations, when we talk about infinitesimal quantities. So the other term is a higher order term. Okay, let me write higher order terms. Okay, we don't work with higher order terms when we deal with infinitesimal quantities. Okay, now if you look at this, this is equal to x vector minus, you see that I divided by h bar is a number, you can pull it out. A number commutes with all operators. So you have got, let me write the rest of it, x vector p vector dot dx vector prime. So I think I'll pull plus I by h bar outside. Okay, so it's minus x vector p vector dot dx vector prime plus p vector dot dx vector prime multiplied by x vector prime operator. Sorry, x vector operator. Okay, or the position operator. All right. Now sometimes when I say these things, I might miss the word operator. I may simply say x vector, but you remember that it's an operator. Okay. Now what do we have here? We have got p vector dx vector prime x vector minus x vector p vector dx vector prime. This is nothing but the commutator of these two quantities. So this can be written as x vector plus I by h bar and the commutator of p vector dot dx vector prime comma x vector. Okay, so that's the result that we have here. X vector goes to x vector plus I divided by h bar multiplied by the commutator of p vector dot dx vector prime comma x vector. Okay, now we have to evaluate this commutator. Let's evaluate this commutator. P vector dot dx vector prime, p vector operator dot dx vector prime comma x vector operator. Okay, now you note that p vector is a vector operator. It has three components. Okay, so we can write it as a vector operator like this. We can write p vector is equal to px operator I hat plus py operator j hat plus pz operator k hat. Okay, and x vector operator can be written as x operator I hat plus y operator j hat plus z operator k hat. Similarly, this dx vector prime is the infinitesimal vector, infinitesimal displacement denoted as dx prime I hat plus dy prime j hat plus dz prime k hat. Note that the notation that we have been following is like this. For operators, we use unprimed quantities. Okay, there's no prime for operators. Whereas if we are dealing with numbers or infinitesimal quantities, etc., we use primed quantities. For example, the eigenvalues are given using primed quantities. Okay, so the prime here in our notation actually says that this is not an operator. All right, whereas this p vector and x vector are operators. All right, now let's substitute these things. So p vector dot dx vector prime. Okay, so the dot product of these two terms gives us, this is px dx prime plus py dy prime plus pz dz prime, the usual scalar product of two vectors. Okay, so momentum vector has three components. So if you take the scalar product with dx vector prime, which also has three components, you get this expression. All right. So this is the commutator of p vector dot dx vector prime. This is px dx prime plus py dy prime plus pz dz prime, comma, x vector. All right. X vector is xi plus yj plus zk. All right. So this is the commutator that we have to evaluate. All right. Now, if you remember this is a fundamental commutator. All right. You have to remember its value. You know that commutator of x with px is ih bar. All right. So you may remember this. We have got commutator of x with px. This is also equal to commutator of y with py. This is equal to commutator of z with pz, and all this is equal to ih bar. Okay, and all other terms are zero. Commutator of x with py is zero. Commutator of y with px, etc. are zero. I think we compactly wrote it like this. Commutator of xi with pj is ih bar delta ij. It's ih bar delta ij. Okay. So if you have x and py or x and pz or y and pz or y and px, etc., all these terms are zero. Okay. So let's expand this commutator. We have to take all the terms, the commutator of all these terms, but we need to take only non-zero terms, because we know that the only non-zero terms appearing here are the commutator of px with x, the commutator of py with y, and the commutator of pz with z. All other combinations are zero. Okay, so let's write it like this. This is the commutator of px with x. Okay, px with x, there's a dx prime here and an I hat there, so it becomes multiplied by dx prime I hat. Okay, plus let's take this commutator, because all other combination of px with the terms here are zero. Px with y is zero, px with z is also zero. Okay, so next non-zero term is commutator of py with y. Okay, and then we have got dy prime j hat plus the next non-zero term is pz, commutator of pz operator with z, and then multiplied by k hat. Sorry, there's also the dz prime k hat in here. Okay. Now we know that x with px, the commutator of x with px is ih bar. That means that the commutator of px with x is minus ih bar. The commutator is antisymmetric. Okay, so this is minus ih bar. Similarly, this is also minus ih bar, and this is also minus ih bar. So let me take this minus ih bar common outside from all these terms, and we have dx prime I hat plus dy prime j hat plus dz prime k hat. Okay, now what is this? This is nothing but our dx vector prime. Okay, so we have got this equal to minus ih bar dx vector prime. Okay, so this commutator, what we have found is that this commutator p vector dot dx vector prime comma x vector is minus ih bar dx vector prime. You substitute that here, I multiplied by minus I gives plus 1. Okay, h bar and h bar cancel, and you are simply left with dx vector prime. All right, so here we see that under this unitary transformation, the operator x in the second approach goes to x vector plus dx vector prime. Okay, I hope this is clear. The most important thing is that both these approaches lead to the same result for the expectation value of x vector. So if you ask the question, how does the expectation value of an operator change under these unitary transformations, then both these approaches give the same result. Okay, so this is something that we can access in a measurement. All right, we can check how the average values change under a certain unitary transformation. Right, and it doesn't matter which approach you use, you'll see that the prediction for the change in expectation value is exactly the same. All right, now we can easily check this. So let's do it in approach 1. All right, so in approach 1, let's say that the initial or the expectation value in the given state ket alpha is ket alpha operator x ket alpha. All right, so this is the definition for the expectation value in the state ket alpha. All right. Now we know that under translation this goes to, in approach 1 we know that ket alpha goes to u acting on ket alpha, or in this case it's a translation operator acting on ket alpha. Okay. And bra alpha correspondingly goes to bra alpha multiplied by T dagger. Okay. So you see that the expectation value here goes to bra alpha. I'm using approach 1. So this goes to bra alpha T dagger x vector ket alpha. Sorry, there's a T ket alpha, the translation operator acting on ket alpha. Okay. Now this is something that we calculated in the previous slide. T dagger x operator T, this is equal to, we showed that this is equal to bra alpha, because using associative axiom, it doesn't matter which of these multiplications you carry out first. Either you can carry out these multiplications first, or you can carry out this multiplication. All right. So we can write this as, using the associative axiom, we already found the result for this. We saw that this is equal to x vector plus dx vector prime. Okay. Now this is equal to, you see that bra alpha x vector ket alpha plus bra alpha dx vector prime ket alpha. Okay, this is the only operator here. Dx vector prime is not an operator, but still we can write this as expectation value of x vector plus expectation value of dx vector prime. Okay. Now, if you look at approach 2, you get exactly the same result. Okay. The only thing is that we'll start with bra alpha operator x ket alpha. Now we retain bra alpha like that, and instead of x vector operator, we now write T dagger x vector operator T and then ket alpha. You see that it's exactly the same thing. So it will again give us expectation value of x vector plus expectation value of dx vector prime. Okay, so both these approaches give us the same result when we are talking about something that we can measure. Right? For this reason, both the approaches can be used interchangeably. Okay, either in the first approach, either you keep the state gates the same. Sorry, in the first approach, you keep the operators unchanged and change the state gates. All right. In the second approach, you change the operator, but you keep the state gates unchanged, and both approaches give the same result for the change in the expectation value. Okay. Now both these approaches can be used in the case of time evolution also. Right. It's exactly the same logic. And if you use the first approach, then this approach is called the Schrodinger picture. And if you use the second approach, where the operators change in time and the states remain unchanged, it is called the Heisenberg picture. All right. In the next session, we shall discuss these two pictures in more detail. But I hope the basic idea is clear. Okay. Thank you.